Okay, welcome everyone. We continue to lecture 3 of IMSE881 linear programming. This part we talk kind of review the simplex method itself in a conventional way, and then we started from here and to explain how can we streamline the implementation. Right, let's do, and this example of a simplex method handouts coming out of page 22 to 29 of our handwritten handout. Okay, we're giving you the first example model. Example model maximization of maximize of 5x1 plus 3x2 subject to a two constraint, 3x1 plus 5x2 less than equal to 15, 5x1 plus x2 less than equal to 10, x1 and x2 are non-negative. We can adding the slack variable to my system to make it equality constraint. So x3 and x4, okay, added into the constraint, make it equality. Also, the x3 and x4 bearing no impact to my objective function. In order to convert this into a standard linear programming format, we need to convert it into a minimization problem. So we're going to minimize z, where z plus the original objective function equal to 0. So z going to take any negative value of the original objective function value. We can take easily moving the the original objective function into constraint, and we can actually, and the rest of the part is just constraint matrix and vector format, and all the variable x1 through x4 are non-negative, and we can put this easily into a linear programming simplex tableau. The next slide showing this, the first row, and z has 1 in the first rows, 5 3 0 0. Accordingly, right hand side is the current objective function value over here, and the rest of them, the first row and second rows, are the original constraint function and layout in the tableau format. Initially, we have A3 and A4, which is the column corresponding to x3 and the column corresponding to x4 are the bases. So here I have A3 and A4, and the right hand side to begin with. So for this, we're going to choose a pivot column, which is the maximizer of the positive portion. Okay, based on here we call the zj minus cj minus zj, and that's the column has a maximum positive value. So therefore we choose x1 as entering. Then based on the minima ratio test, okay, we're taking the right hand side divided by the column right here with only positive number. So 15 divided by 3 will be 5, 10 divided by 5 will be 2, so 2 will be the smallest value. So therefore x4, which is column 4, a column corresponding to x4, is the outgoing leaving variable. So we can set up the similar equivalent system. So here is the 35 times x1, 35 times x1, 52 times x2, 10 times x3, 01 times x4 equals to the right hand side 15 and 10. If I using x3 and x4 are the currently basic variable, so basic variable x3 and x4, and moving x1 and x2 to the right hand side of the equation. So 15 minus 3x1, since x1 is entering, So x2, since it is not non-basic variable, and it stay non-basic for the next iteration. So 15 minus 3x1 and 10 minus 5x2, both of them has to be non-negative. So we can list over here. So x1 has to be less than equal to 5, or x1 has to be less than equal to 2. So therefore, x1 will be entering basis, x4 leaving the basis, and the next iteration, x1 will be equals to 5, and x4 will take a value of 0 and leave the basis. And how are we going to demonstrate how we're going to pivot? So we're going to pivot is we're going to make this column exactly looks like this, the original x4 column. So it's a 0, 0, 1. So we're going to make this column looks like that by using the 3 different elementary row operation, either divide the whole row, or exchange row, or multiply a number for a row and add it to another row. So these are the 3 elementary row operation after. So look like the pivot. We're choosing a zj minus cj less than equal to 0. Here is the cj minus zj. So stop. And this is for minimization problem. Or else pick an entering variable xk based on zj minus cj greater than 0 and the largest one. Okay, so we're choosing a greatest that one. And in our case will be z1 minus c1, which is 5, and maximize is the maximize of 3, 5, and 0. Column AK entering the basis if at least one of the yk is positive. The yk, which is 3 and 5. Okay, A1 entering basis, so x1 is going to be the entering variable. Then we'll perform a minima ratio test based on the taking the right hand side divided by yk. Okay, yk is the current tableau, the columns of entering variable. So B2, which is A4, which is A4 are leaving. Okay, and the B2 equals to A4, which is X4 leaving the basis. Next iteration, we can look at it. After pivot, the X1 column looks like the X4 column used to be, and by doing pivot, we call it pivot. Basically, it's an elementary row operation. So, and by look at this, we still have a positive zj minus cj portion. And then we choose x2 as the entering, so a pivot after that to make a next tableau exactly looks like an x4 column. And then we're going to choose x2 as the entering. This is the only one positive zj minus cj, and we can choose that as. Then we take a right hand side, okay, right hand side divided by the yj column, y2 column basically. And then we got 45 divided by 19, and 1/5 divided by 2/5, and that's 5. So between these two, this is the minima ratio. So therefore, we say that x3, which is A3, leave the basis. Okay, and that's the pivot column, and that's the pivot elements. Usually we say that. So we want to using again the elementary row operation to make this x2 column exactly look like the x3 column. So we're going to divide this by 5/19, and then make these two elements to be 0. Equivalent system, what we have is basically z plus x2, okay, z plus x2 minus x4 equals to -10, and that's the current objective function value. 19/5 plus x3 minus 3/5 of x4 equals to 9. x1 plus 2/5 of x2 plus 1/5 of x4 equals to 2. So we can actually, from the simplex tableau, write out the corresponding linear system. And since x2 is the interim variable, we can move x2 into the right-hand side, and seeing the x3 and x1 equals to what? So 9 minus 19/5 times x2 greater than 0, 2 minus 2/5 of x2 is greater than 0. So we can actually simplify. x2 has to be less than or equal to 45/19. And that will be, then the next iteration, x2, we're going to take a value of 45/19, and x3 will be coming, the non-basic variable, take a value of 0. So let's take a look how we're going to do next step. So next step, we'll make this column identity column, and x3 and x4 now are non-basic variable. Take a look at the gray rows. This is the first row, zj minus cj row, and they are all negative right now. And the equivalent system looks like the following. So z minus 5/19 times x3 minus 6/19 of x4 equals to negative 235/19. Okay. And we can check that. If we move these two elements out of to the right hand side, we have negative 235/19 plus 5/19 times x3 and plus 16/19 times x4. If we increase either x3 or x4, actually, we are going to deteriorate the objective function z, since both of these are positive. So there's no way I want to introduce x3 and x4 into basis anymore to improve my objective function. And at this point, we know we are reaching the optimal solution, and we can stop our algorithm, and we can write out directly the current basic optimal basic feasible solution, and which is x1. Okay, x1 equals to 20/19, and x2 equals to 45/19 right here, and then x3 and x4 are non-basic variable now, and at the optimal taking values of zeros. So there's no way we can improve this objective function anymore, so we stop our algorithm. We know we reached the optimal solution. We can also perform exactly the same thing using matrix algebra. I'm not going to spend too much time at this moment to explain this, because I can show you, we can form, each time I form a basis B, and I can take a B inverse. Once I have the B inverse, I can perform, calculate the corresponding basic feasible solution, calculate the corresponding objective function at that iteration, and we can calculate the yj column. What are the yj column? Yj columns are basically, yj columns are what? And the current tableau for each one of the non-basic and basic columns in the original constraint location. The yj column, actually, same thing here, yj column. For the basic variable, their yj column equals to identity column. However, for the non-basic variable, their yj column is not, they are not identity column, and so on. So, and also we can with the basic yj column, I can revert it back into the original constraint if we want to. And we can calculate the corresponding zj minus cj. Okay, zj basically equal to cb transpose times yj minus cj. So also yj equals to b inverse times aj, so right here. Okay, as we have right here. And this method is traditionally called the revised simplex method. And this is the way we want to implement this whole thing, the simplex method, in a computer. And we're going to show you later on, but here I'm just quickly run through. You can actually, based on one piece of information with a new basis, once you calculate B inverse, then you can revert the current, calculate the current variable simplex tableau if you wanted to. And you can also use that to revert to the original simplex tableau or the original problem set before even perform any of the pivot. So this method is implied as we call the revised simplex method. You see that is much more streamlined and just using matrix algebra to calculate the solution. And the algorithm is exactly the same. However, we've only performed the necessary matrix calculation. This slide, I want to summarize our simplex tableau. I want you to kind of have a memorization of this tableau because later on we're going to throw away the simplex tableau format because it contains too much of the information we may not need to have efficient calculation. But right now we just want you to kind of memorize or visualize whether the value actually you on the simplex tableau every time we mention something. This is a standard simplex tableau. The first column has a 1 in the z position and rest of them 0. x1, x2, xn are the original variable. And we call this row 0, basically, row 0. And for each one of the row 0 on the corresponding axis equals to zj minus cj rows, okay, column. And the right-hand side, z equals to actually cb transpose times b inverse times b, because equals to cb times xb. And xb equal to b inverse times b. B is lowercase b represent the original right-hand side. And b inverse is only thing change each iteration if you change basis, basic matrix. Again, yjs are y1 to yn are b inverse times the original constraint of aj. So y equals to b inverse times aj, okay, all the column here. Many times we're going to refer them as y columns, okay, and equals to b inverse times aj, wherever aj is the ith column of the original A matrix, original constraint matrix. And zj up here, and column 0, equals to cb transpose times yj, okay, cb transpose times yj. And also equals to cb transpose times b inverse times aj, because b inverse times aj equals to yj. And cb is a vector, cost coefficient vector corresponding to the basic variable. That's all there's to it. So this is kind of important slide, but I want you to be able to visualize Later on, we're going to throw away the simplex tableau and calculate each one of those separately. But you need to remember each one of these numbers where they are on the simplex tableau. The current basic solution always B inverse times B, remember that. And the current objective function is supposed to be CB transpose times XB, which can be translated into B inverse times B. And the ZJ is equals to CB transpose times YJ equals to CB transpose times B inverse times AJ. And AJ is the original matrix. So you really don't need any more information. All you need is the original data from the simplex tableau or the problem itself, knowing what are the current basic columns, which are forming the basic matrix, and calculating the B inverse. And based on the B inverse, you can recalculate the entire simplex tableau that way. So this is a little bit more streamlined thinking of the original simplex tableau, and it is more less computational requirement for the original simplex tableau. The next slide we're talking about reduced cost lemma. How do we calculate reduced cost, which means how do we determine what is the entering variable, which non-basic variable to entering the basis next iteration. So let's take a look. So let B is the basic matrix with a variable number arranged in such a way. B matrix in the from, and the non-basic matrix in the rest of the column. So the basic matrix has a B1 to Bm. So this basic matrix has an m by m dimension, so have a m column. But the n plus 1 column in the original A matrix to the an column, to the nth column, belongs to the non-basic. Okay, so we're going to use this to kind of illustrate the so-called how do we pick which one, which non-basic variable to entering the basis. Again, for the notation summary, we can separate the C vector, the cost coefficient vector, into CB and Cn. It's the cost coefficient corresponding to the basic variable and the cost coefficient corresponding to the non-basic variable. Same thing for the basic variable separation with a non-basic variable. So if I have a basic feasible solution X and it is a corresponding objective function value Z hat, okay, Z hat usually in this theory we refer as the current objective function value, so we make a note of that, and actually equals to CB transpose times XB. Of course, it should be also plus Cn transpose times Xn. However, this part, Cn transpose times N is, however, actually the Cn transpose times Xn can be ignored since Xn are all currently set to 0. So therefore, the current objective function value equals to CB transpose times B inverse times B. The B inverse times B is actually the current basic feasible solution. Look at the Zn corresponding to the non-basic column. Zn basically is this guy's, okay, ZJ's, I'm sorry. We're going to calculate in Zn. Why I use Zn? Zn is the calculate the Z corresponding to the non-basic column, and actually equals to CB transpose times B inverse times N, and basically are these guys involved. So CB transpose times B inverse times A column n plus 1 column to the A nth column, which is B inverse times all these guys. And actually they are equals to the y n plus 1 column and the 1a column as well. So those are the z corresponding to the non-basic variable. Okay. So if we want to finding an x prime, which is any other feasible solution, then we can calculate a z prime, which is a new objective function, since this is x prime is a different solution from x. Look at the z prime. The z prime equals to c transpose times x prime, and equals to the differences. For example, the z hat, which is the original objective function, minus zn minus cm, so times x prime. So whatever changed from the non-basic portion to xn is come into play. So therefore you can see that we can formulate it into a some explicit format of the z has the original objective function minus this portion. So what we do is, since we are dealing with a minimization problem, what we need to do is trying to find if zj minus cj, I know xj prime later on will be 0 or a positive value. So if I choose zj minus cj as a positive, I can reduce my current objective function. If zj minus cj is negative, so negative plus times something positive, and have minus sign right here, actually I increase my objective function, which is not what I want. So therefore the zj minus cj is referred as the reduced cost for the objective function value. So zj, if xj increased by 1, or other non-basic variable remains 0, then we can improve my objective function. We can lower my objective function in that case. So let's take a look how the proof is. We're going to plug in x prime, which is a new feasible solution, and separate them out between b and n, and moving this part and multiply both sides by b inverse. Okay, so xb prime can be calculated in the way b inverse times right hand side b minus n times xn prime, and we can calculate that as well. So b inverse times b is the current basic variable xb, and this part will be b inverse times xn. All right, and we can calculate z prime. Z prime is the new objective function corresponding to x prime, equal to c transpose times x prime equals to cb transpose times xb prime, which is this part, and plus cn transpose times xn prime. Okay. And the first part we can separate that out by this equation. So what do we do is b inverse times b minus negative b inverse times n times x prime n, xn prime, plus cn transpose times xn prime. Basically what I'm saying is the new objective function value corresponding to x prime equals to c transpose times x prime equals to cb transpose times xb prime plus cn transpose times xn prime. So we're going to replace the xb prime using this equation. So plugging in this equation, we're getting from the constraint equation. So this will be cb transpose times this plus cn transpose times xn. Then we can actually expand it further. So the first part right here is a CB transpose times B inverse times B minus, okay, CB transpose times B inverse times N. N is the n plus 1 column to the n column times X prom plus a Cn transpose times X prom. So we can basically collect Xn prom column and make it happen. Okay, so this is pretty much the original. This part is the original z hat, which is the original objective function, because B inverse times B are the current basic solution corresponding to X before we introduce X prom. And CB transpose, which this part equal to z hat, and this rest of the part equal to the zj minus cj times xj. Xj are the non-basic variable. Okay, so with this negative sign right here, I just want to choose the positive zj minus cj for some of the non-basic variable and introduce them as as the basic variable. However, if we find out all the zj minus cj for current non-basic variable xj prom are less than or equal to 0, then I can see that z prom, which is a new objective function, is going to be greater than or equal to the current objective function. So there's no point to introduce any more non-basic variable. The x currently is the optimal basic feasible solution. So that concludes the, the proof of the so-called famous reduced cost lemma, how we choose interim variable in the simplex method. I'm going to finish this video. We continue the rest of the slide on another video.